Thanks a lot, Richard. It's great to be here. It's always hard to follow the Mads Dustin show. They're wonderful to watch, but I will try to do my best. There's nothing I like more, at least in the technology world, than talking about making things fast. And there is a lot to talk about in terms of making things fast in .NET 7. As some of you may know, I've taken it upon myself every year for the last 5 years or so to, towards the end of each .NET release, getting ready to ship, sort of documenting the myriad of performance improvements that have gone into this release. And I did that again this year in August. And if you were to print it out, it comes out to more than 200 pages, just sort of highlighting how much stuff from a performance perspective has gone into this release. If you haven't read it, I'd encourage you to. But the reason I bring it up is to say there are huge numbers of improvements. There were over 500 pull requests and improvements discussed in this PR. That's only a subset of the ones that there are. Obviously, I'm not going to talk about 500 different performance improvements in the course of 25 minutes. So instead, I've pulled out just a representative few and sort of tried to up-level them a bit to look at them through sort of a lessons learned, or how we think about the kinds of performance improvements we want to make in a given .NET release. And I should say, when I say we here, I don't just mean those of us on the .NET team or those at Microsoft. Many of these performance improvements, over a fifth of these performance improvements, have come from folks outside of .NET, outside of Microsoft. We have a wonderful .NET community, and if you're not already participating in the .NET repos, I would highly encourage you to do so. So with that, let's dive in. So the first sort of category here is about trade-offs. For those of you who aren't familiar with the English idiom of having your cake and eating it too, it's all about having two things that are sort of diametrically opposed, and you find a way to have both of them rather than having to choose between them. And a really great example of that when it comes to .NET and managed languages typically in general is around JIT compilation. So with a JIT, where you're compiling all your code as part of the process's execution, you have this trade-off to make between how much time do you spend fully optimizing your code and how much time do you spend at startup. So you want to get really great code quality, but that requires more time to compile it, to analyze it, which then negatively impacts your code actually getting going. So one of the technologies that was introduced in .NET Core 3.0 is tiered compilation. This is an instance of having our cake and eating it too. With tiered compilation, we actually allow the JIT to compile a given method multiple times. It can compile it once and do so with basically few optimizations enabled, as few as it can muster, such that it can compile it really, really fast and doesn't have to spend any time on analysis and optimization. And then if it finds that that method is on a hot path and it's getting invoked over and over and over, it can recompile it, this time with all the optimizations it can possibly throw at it, backpatch the application such that all further invocations take that highly optimized route. And this gives you a really great startup without sacrificing code quality. In fact, you can even get better code quality with this, because when the JIT does that initial what we call tier 0 compilation, it's able to instrument the code for a variety of things. Not only can it instrument it for the number of times the method is being invoked in order to determine when it needs to tier up, but it can also instrument it for other things. For example, with a given interface, what is the concrete type that is typically being used for that given call site, and it can optimize based on that, and other things that it can learn about the method from that initial invocation. Now, the problem where we haven't been able to have our cake and eat it too is that this doesn't apply to all methods. There's a category of methods that could actually be really important for throughput, that could be really long running, where optimizations could be really valuable, but that aren't frequently invoked. And if you imagine a method that has a loop, you could be sitting in a really tight loop doing a whole bunch of processing, but only invoke that method a few times or even once. Your main method, for example, is typically only ever invoked once in your process. And so by default, tiered compilation was disabled for methods with loops until now. So in .NET 7, there's a new technology as part of the JIT called on-stack replacement. And this, again, lets us have our cake and eat it too. In addition to tracking how many times a method is invoked, it also instruments loop iteration counts. And when a loop has iterated enough times, the JIT is able to generate a brand new optimized version of the method, jump from the unoptimized code into the optimized code, transferring over all the relevant local state, and continue executing there. And as a result, we're able to have tiered compilation for all of these methods, including ones with loops, which we couldn't in .NET 6. So let's take a look at this. I've got a very simple example here trivial code, not something that you would actually write because it's computing something you already know. 10,000 times we're looping through all of the characters 0 to 65,000, and we're checking and counting how many of them are ASCII digits, basically the numbers 0 through 10. Obviously, the answer is 10. We don't really need this to compute it, but it's some computation to make an example out of this. So let me run this. I've got I'm going to build this for .NET 6, and I'm going to build this for .NET 7, and then I'm going to run this on .NET 6. And when I do so, we can see it's computing an answer of 10, and it's taking just over half a second to do this computation. Now, this is with tiered compilation, but loops are off by default. And if we saw my method here, it's just a main method with a big loop calling this little helper function, but this function is only ever going to get invoked once. Now, if I were to override that default and I were to set .NET TC quick JIT for loops, now I rerun this, and we can see because that main method was opted into tiered compilation, now it's taking over a second because it's unoptimized, but it's not being invoked enough times to tier up to tier 1 with fully optimized code. If I instead run this now with .NET 7, note I'm not unsetting this environment variable, which is actually set by default. Now when I run this in .NET 7, not only is it not taking a second, but it's taking even less time than it did on .NET 6. So now it's taking less than half a second to compute the same results. And more so, I can even fully understand what's happening by taking advantage of another set of new features in the JIT, which is that the JIT can now tell us information about what it's doing and when. So I can say .NET JIT disassembly summary equals 1. And now when I run this, we see that the JIT has output a line for every method that it compiled. Now, obviously, in order to run hello world, it's actually there's actually more than 7 methods that are running as part of my application, but most of them are coming from the ready-to-run images that are shipped as part of the core framework. The JIT had to compile these 7 methods for a variety of reasons, and we can see one of them is my main method, and indeed, it started out at tier 0, and then because it was executing the loop so frequently, it very quickly tiered up to a tiered 1 with on-stack replacement. And in fact, I can go further than this. I can say not just JIT disassembly summary, but I actually want to look at the assembly code that's generated for my main method. Now, when I run this, I will see that there are 2 blocks of code very quickly spit out. And if I scroll up through this, all this assembly code here, I can see that first, I have an assembly code output for tier 0 compilation with minimal optimization. And we can actually see that these optimizations aren't kicking in. If I scroll down a bit, we can see that there's a call to that one-line trivial helper function, which you would normally expect to be inlined. But inlining is one of the optimizations that's disabled as part of tier 0. So in my unoptimized code, I see that I indeed have a call to that function. If I then scroll down to my next block of code, we can see it rejitted that method. Now it's using optimized code. And if I scroll down to approximately where we saw that call, now I see these few instructions. And if you know your ASCII table, the character 0 is decimal value 48. So this is that inlined is ASCII digit, subtracting character 0 and comparing against the number 9. So on-stack replacement and as part of tiered compilation is a really welcome addition to .NET 7. Another example, another category of lesson learned is if you're writing libraries, you're writing services, you'll often deploy, and then you'll find that your consumers end up having to sometimes rewrite the same functionality over and over as part of consuming your work. And an example of this comes with reflection invoke, for example. So reflection invoke, you use reflection to get something like a method info, and then you want to dynamically invoke it. So you call method info.invoke, you pass in your object array of arguments, you get back your object result. It's very dynamic. It's also relatively expensive. And in order to work around that expense, we found that a variety of consumers of .NET, including ourselves and our own libraries, were spending a little bit more time at startup to use reflection emit to actually generate custom little invocation stubs where once at runtime we learned what we needed to know about the method, we could generate a custom invoker just for that method, and then we would have a delegate to that custom invoker that would make it really fast. Well, we don't want everyone having to re-implement all that functionality themselves. So in .NET 7, we've implemented that as part of reflection invoke. So I have a simple little demo here. I have two methods, one that has 0 arguments, one that has 1 argument, and I'm just doing a benchmark that over and over is going to invoke them using reflection invoke. And if I compare the runtimes here for .NET 6 versus .NET 7, we see the 0 argument version where on .NET 6 it was taking about 45 nanoseconds. It's about, what, 7 times faster, 6 times faster on .NET 7 by having this reflection emit functionality built in. And similarly for the 1arg method, with what was taking 82 nanoseconds on .NET 6 is taking about 20 nanoseconds on .NET 7 for about 4 times faster. And this is just one of those things where you upgrade and all of a sudden, if you're doing this, in really hot loops, you're going to notice a performance boost. Moving on, another category that is sort of near and dear to my heart is it's really easy after you've implemented a solution to a problem to forget that all the research you did, things may have evolved since then. And there might be a better solution available to your problem. And you can see all the research going on in academia and in various corporate think tanks and work groups. There's a lot of interesting research happening in computer science that we need to reconsider every release. Are there areas we could improve based on that research? So one example where this impacted .NET 7 is some research from MSR, actually, Microsoft Research, that's gone into our regular expression engine, or some really nice new math, basically, that came out of, I believe it was JP Morgan Chase, around how to do some math around calendars that's allowed us to improve some of our core primitives in date time, getting the month, day, year, stuff like that. And then some lovely work out of a professor in Canada, Professor Daniel Lemire, who he and some of his associates came up with an approach for parsing floating point values about twice as fast. And that is now built into .NET 7 as part of double float triparse. So let's dive deeper into one of these, in particular, regular expressions. So some of you may remember back in 2016, there was an outage at Stack Overflow, where for, I don't know, it was 20 or 30 minutes, the system was down. And Stack Overflow released a really nice postmortem after the fact, detailing what went wrong. And what went wrong was a regular expression that hadn't been fully validated for its performance characteristics, getting past a particular input that basically spiked CPU on all the front end tier servers. So what I've done here is I've just extracted the details from that postmortem. I've got the particular regex here and the particular input they described, which was basically 20,000 characters. And in the bad case, it was 20,000 characters that did not end in a white space. And now I've run this on .NET Framework 4.8, .NET 6, and .NET 7 using the good input. So we have two inputs here, a good input and a bad input. And now if we look at just the good input, we notice something really nice. .NET 6 is about 10 times faster than .NET Framework 4.8. .NET 7 is about, what, 15% faster than .NET 6. Yay, we're making forward progress. Now we try the bad input. And the good news is .NET 6 is still about 4 or 5 times faster than .NET Framework 4.8, and .NET 7 is more than 2x faster than .NET 6. Woohoo! You can see the downside here, or the bad news. The bad news is all of these numbers are like 14,000 times worse than the good input. There's this huge disparity here. And that's what this research has gone into address with a new option in .NET 7 that is regex options.non-backtracking. This is a fully implemented engine that's able to support most, not all, regular expression constructs. But if you limit yourself to that subset, it has this exact same semantics as if you're using the regular backtracking engine, so you can switch back and forth. And the important thing two important things to note, actually. First, for the good input, it is a little bit slower than at least the .NET 6 and .NET 7 implementations. In this case, for this particular input, it's about 5x slower. So this isn't always necessarily going to give you the best performance. However, you notice that for the worst case, it is orders of magnitude faster than all of the other numbers. And in fact, it is exactly the same whether it's a good input or a bad input, subject to minor noise in the benchmarks. And that's the really important thing with this option. You get the same semantics as with the backtracking engine, but you get consistent performance regardless of the input that's being provided. Some really exciting work in .NET 7 here. Another category of work is sort of or of improvements is thinking about all the places that we can reuse existing functionality. As developers, we like to kind of hand roll things, but often if you just take advantage of the built-in helpers for things like searching with index of, every release, when we make those operations faster, anyone who's relying on those operations themselves gets faster. And so we've done work in this release to not only improve those primitive operations, but also use them in as many places as we can in our own code, such that not only your code using it gets faster, but our code using it gets faster, and then your code using those indirect uses gets faster, and so on. So here's a simple example. We did some improvements in the vectorization of index of, for searching strings, spans, etc. In this particular case, I've got the complete stories or works for Sherlock Holmes from Gutenberg, and I'm searching for elementary, my dear Watson. And you can see in this particular case, when I search for elementary in .NET 6, this was taking about a millisecond, and on .NET 7, it's taking only about 57 microseconds. So a huge improvement there. It's a 20x. Because we're doing a better job of figuring out exactly what to search for and how to vectorize that search. Similarly for ordinal and nor case, we're also employing a better form of vectorization now, and so this also gets about four times faster. Continuing in that theme of taking advantage of these helpers, any place where you're not, it's worth reconsidering, are there workarounds that you've employed where you'd be better off just getting rid of your workaround and going back to the original thing. So here's an example of that. This comes from some real code, which I've simplified down. If I want to look to see whether a URL begins with https://, I can use starts with, ordinal ignore case, because I don't care about whether it's capital HTTP or lowercase HTTP, and so on. Now, at some point, when someone wrote this code, they must have benchmarked this and realized that they could do it faster if they just open coded it, if they just did it themselves. So we have they're checking the length here to make sure it's at least 8 characters. Then they're doing some really cool ASCII tricks, recognizing that the uppercase ASCII letters differ by only 1 bit from their corresponding lowercase letters. So if I just OR in 0x20, I can do a single comparison for each. And they probably benchmark this. And in fact, when I benchmark this on .NET Framework 4.8, I see indeed the open-coded one is 10 times faster. Woohoo! Good day's work. 2 nanoseconds instead of 20 nanoseconds. But then let's say we run it on .NET 6. Well, it's still faster, but both of the numbers have actually gotten faster. The 21 nanoseconds has dropped to 6 nanoseconds. The 2 has dropped to 1. Still better, but is it worth it? Maybe. Depends on the use case. Now we go to .NET 7. And now not only is the open-coded version way more code to maintain, it's also twice as slow as the built-in implementation, where the JIT is now recognizing these patterns and is able to generate the most optimal implementation it can muster for the simple version of the code. And so anytime you're employing these kind of workarounds where you want to revisit them and figure out whether we can just make the central thing better, everyone can use the central thing, and anytime it gets better, everyone's code gets better. And speaking of getting better, another important lesson is no matter how much you've optimized, there's always more opportunity. There are always new things you haven't explored. Maybe there are improvements elsewhere in the system that you previously dismissed because they're too slow, but now they're actually highly optimized and you can take significant advantage of them. And a great example of that, again, comes from regular expressions. So here is this particular benchmark. Isn't actually one that I came up with. This is from an open source repo that's comparing the performance of regular expressions across a whole bunch of languages and frameworks. So I've just copied that expression as well as the input that repo is using. And I'm counting how many times an email address, which is what this expression is meant to find, occurs in this input text. And if I run this on a variety of previous releases of .NET, we can see on .NET Framework 4.8, this was taking about a second. You go to .NET Core 3.1, it improves by about 10%. That's pretty nice. You go to .NET 6, and oh man, it gets what, about 20x faster at about 49 milliseconds. And then you go to .NET 7, and it gets even orders of magnitude faster at about 620 microseconds. But then there's even more opportunity. So One of the things we've done in .NET 7 is introduce a bunch of additional methods onto regex for doing both specific operations like counting, which is what I want to do here, or enumeration without actually allocating, sort of amortized, non-allocating matching with regexes, as well as be able to pass in spans that I can slice or get from wherever it may be. Maybe I stack allocated some memory, or maybe I got some data from native code. I no longer have to copy it into a string to search it. I can just pass a span directly into the regex engine. And now when I just change the code to use this simpler code, it's also faster. It got about 20 microseconds faster, and you'll notice that lovely allocated column is blank. That's because there was nothing allocated as part of this operation. So there is always more opportunity. And then finally, one last category to think about, and there are many more than this covered in the paper, but one more for this presentation, is being thoughtful about your defaults. And we strive, when we design APIs, when we design language features, we try really hard to come up with good defaults, where if someone uses something, they're going to get kind of really great average case behavior, average case performance out of the box. We don't always get it right, and I imagine you don't always get it right either. So it's worth thinking about those defaults both for new things and revisiting previous choices. And an example where we revisited a previous choice in .NET 7 is with compression, and specifically with Brotli compression. Brotli is a compression algorithm from Google. We've been shipping an implementation, a Brotli stream type and Brotli encoder and decoder in .NET since I believe .NET Core 2 or 2.1, around there. And if you look at the Brotli compression algorithm, like many compression algorithms, it has a knob you can turn, a dial. In Brotli's case, it goes from 0 to 11. And on one end of the dial, you have really, really, really fast compression, but maybe not the best compression ratio. So maybe you end up with a larger output. And at the other end of the spectrum, you have the smallest possible file size or output size it can muster, but it might take a really long time for it to figure out how to optimize it fully. Now we can see I benchmarked both size and time on a particular file in this case, and we see from 0 to 11 a nice sort of linear progression. Excuse me. As I turned up that dial, going from about 2.5 megabytes down to about best compression ratio down to about 1.7 megabytes. But on the time, we see not so nice a linear scale. In fact, towards the upper end, it starts looking extremely exponential. Now, the problem is that in prior to .NET 7, we chose a default of 11. Which meant that by default, if you just said new Brotli stream, you were getting the rightmost side of these graphs. That meant best compression possible, but also absolutely abysmal throughput. So with one of the smaller significantly performance impacting changes in .NET 7, we basically changed our default from 11 down to something more in the middle, around 4. Now, this does mean that by default, your output sizes might be a bit larger. In fact, if I run a simple benchmark, we can see that for this particular input, the resulting output is about 20% larger than previously. Now, all you have to do is set a compression level, and you can get exactly back to what it was before. So we're just changing the default. But in exchange for that 20% increase in size, we have about a 50 or 100x, about 50 75, I don't know, I can't do math off the top of my head, somewhere between 50 and 100x improvement in throughput. And we think this is a much better use of your time when using Brotli as part of your algorithms. So that was just a really, really quick tour through just the tip of the iceberg. If you have a few moments or maybe a few hours, I'd welcome you to go read the blog post about .NET 7 performance improvements. I'd welcome feedback. We'd love for you to actually get involved and contribute to the next incarnation of that paper by contributing pull requests to .NET 8. Which we've already started working on and which is going to be an amazing release a year from now. So thank you very much.